Hello and welcome back to PC Retro Programmer. In the past couple of videos we've been looking at the application of the CORDIC algorithm to rotation of points about the origin. We saw that if we have a vector to rotate, we just multiply on the left by a rotation matrix involving the sine and cosine functions. Now, of course, naturally one way to do this is to actually compute sine of theta and cosine of theta as well, and then carry out the matrix vector multiply, which itself can be done in 4 floating point multiplications and an addition and subtraction. Now, of course, all of that together is pretty expensive, and so CORDIC tries to save us some of the computation time by simplifying the matrix. You can see that it calls for multiplication by only one trig value, tan of theta, and the other two multipliers are trivial, just multiplications by 1. But we're hiding some complexity here. We also have to multiply by this constant k out the front, which is cos theta, and so we still have two trig functions to compute. And moreover, multiplication by k really means multiply x and y by k after this matrix vector multiplication. And so there are really two floating point multiplications hiding here as well. So you might ask, well, where is the actual saving then? Well, we really won't see this until we deal with the full CORDIC algorithm in a later video. But for our little application here, we're just using a cut down version where we can already realize a pretty big saving. And the idea, of course, is just to choose a value of tan theta, which is very nice, and just put up with whatever value of theta that gives us. So, for example, if we have tan theta equals 1/8 or 1/4 or 1 on some other power of 2, then multiplication by this can just be implemented as a bit shift, which is efficient on a binary computer. And it's especially efficient on a computer with a fast bit shift unit. Unlike the 8086 or the 8088, of course, which can really only shift by 1 bit at a time efficiently. But there are CPUs and coprocessors which can really carry out an n-bit shift just as fast as they can carry out a 1-bit shift, and there the algorithm really shines. But coming back to our application, if we can make the matrix vector multiply trivial on account of the specially chosen value of tan theta, then the only cost that remains for us is multiplication by k. And if we've actually picked a constant value of theta, we can even compute cos of theta using a pocket calculator or by hand if necessary, and just hard code in multiplication by k into our implementation, which is precisely what we've been doing, of course. Anyway, I thought that now might be a good point to insert some information about the importance of CORDIC in the history of digital computing. It turns out that parts of CORDIC were known for hundreds of years, but it really came into its own as a technique in digital computing in 1956 through the work of Jack Volder. In fact, it became known as Volder's algorithm for a while. He was working in aeronautics and he wanted to replace an analog resolver with something that was more accurate, more reliable, and digital. And so the CORDIC algorithm was born. But he also did research into what mathematical functions could be computed using CORDIC, and this included the sine and cosine functions, of course, but it's really amazing how many other functions he was able to extend this CORDIC principle to. So this actually had an effect on the development of the 8087 math coprocessor. It turns out that CORDIC can even be used to implement multiplication and division, and the 8087 didn't have a fast multiply unit in it. Silicon was pretty expensive, and basically there wasn't a very large microcode ROM either, so you couldn't have very complicated functions implemented inside these processors at the time. And so the CORDIC algorithm was actually used to great effect inside the 8087 in place of a fast multiply unit. Now, it wasn't actually used for the functions that you might think. It turns out that the 8087 doesn't have a sine or a cosine function. These weren't really added in hardware until about the 387, I think, when there really was space in the microcode ROM to put a full implementation. Instead, the 8087 offered a partial tan function. So from what I understand, this still implements tan, but just over a limited range, say minus pi on 4 to pi on 4, or if you like degrees, minus 45 to 45 degrees. And then if you want to compute sine or cosine, you have to apply additional floating point operations on top of a partial tan function. And even then, that'll only give you the values for certain ranges of theta. And if you want to do the full range of theta, then you have to do some additional steps on top of that. So actually, computation of sine and cosine on an 8087 could still be quite expensive. I think I computed that to compute sine of theta in the worst case could be something like 1500 cycles. Now, to be fair, if you have a really nice value of theta, it is implemented extremely efficiently in the 8087. But for the general case, it can get quite bad. And if you want sine and cosine, you can get the extra function for not very much extra cost. In fact, I think I worked out less than 2000 cycles in total, and obviously much less for nice values of theta. But yeah, it could still be quite expensive, but the CORDIC algorithm was used for computation of other things, not sine and cosine in the 8087. And the real reason it's used there is because there wasn't a fast multiply unit, as I mentioned. I certainly wouldn't call the multiply unit in the 8086 fast either. It's a very slow multiply unit. It takes something like 130 cycles to multiply two integers. And so you really need a much faster CPU to classify as a fast multiply unit. But this does underscore one of the limitations of CORDIC, and that is if you do have such fast multiply, then there are actually better ways of computing a lot of math functions. So for example, you can approximate them using polynomial expressions, and polynomials are really cheap to compute using fast multiplication. But given the limitations on silicon that we're working with, for this era of microcomputing at least, CORDIC really plays a very important role. And as you'll see later in this video, we can get some really fast rotation results using this cut down version. So obviously we've implemented multiplication by k already, and what remains is for us to do the matrix vector multiply. And then, as I said, we're going to animate a line by rotating it about its endpoint. And that's what we'll be doing for the rest of this video. Let's take a look at the all-important implementation of the main CORDIC routine first. And of course, this is going to do our matrix vector multiplication and then multiply the result by k using our CORDIC mul routine that we implemented in the previous video. And of course it'll call that twice, once for the x and once for the y coordinate. So the main CORDIC routine is down here, and notice that it doesn't take any arguments on the stack. I made the slightly unusual decision to work with values in global variables. We have the coordinates xi and yi, those are the coordinates of the vector that we're rotating. They're 24-bit values, so they're going to take 1.5 16-bit registers each. And so these three lines are going to load those from the global variables in the data segment into registers. And we'll have xi in dx.bh and we'll have yi in si.bl. And I've just written that up here just to remind ourselves exactly where everything is. Now, the first thing that we're going to do is multiply yi by our tan theta value of 1 on 8. This is the same as dividing it by 8, which we do by shifting it right by 3 bits. So after moving some stuff about in registers, these are the lines that do our shifts. So each right shift by 1 bit, it's a 24-bit shift, and so we actually need 2 assembly language instructions to accomplish that. First of all, it's an arithmetic shift. We have to preserve the sign, and that's because the values could be negative. So we use SAR for an arithmetic shift, and we first shift the top 16 bits right by 1 bit. Now, one of those bits is going to be shifted out, and that will end up in the carry flag. and we want to shift that in at the top of the byte that we have to shift. So we have to use rotate through carry for that, and that'll actually take that bit that's in the carry flag that was shifted out of the bottom of DI, and it will shift it into the top of CL, and it will shift everything in CL right by 1 bit. So this is how we perform a 24-bit shift using assembly language. And so, of course, we have to do that 3 times to divide by 8, and that's all there is to that computation. It's really straightforward. So now we're actually in a position to compute xi minus yi on 8, which is really what that top line of the matrix is telling us to do. And so this is just a subtraction, and of course it's a 24-bit subtraction, so we just subtract the bottom bytes, and of course there could be a borrow, and so we have to use a subtract with borrow for the top 16 bits of the subtraction, instead of just using an ordinary sub. And so that's how we do 24-bit subtraction. So now we have xi minus yi on 8. This is actually our new x value. Of course, we have to multiply that by k, but this value is now done other than the multiplication. So the next thing we have to do is the bottom line of the matrix, and the first thing we have to do there is multiply xi by 1 on 8. That's the bottom tan theta value. And again, it's just 3 shifts right by 1 bit, which we do in exactly the same way as we did the shifts above. And so now we're in a position to add xi on 8 and yi, which is what that bottom line of the matrix is telling us to do. And again, the addition is a 24-bit addition, so add the bottom bytes, and there may be a carry, so we have to use an add with carry to add the top 2 words. So now we're done with that, and we have our new y value other than the multiplication by k that we still have to do. So that's all that remains now, just multiplication by k, and so we can call our CORDIC mul for that. So first of all, we do the multiplication of our x value by k, and at this point our x value is in ax.bh, and the nice thing is that the CORDIC mul routine was written so that it takes ax.bh and just multiplies it by k and puts the result back in ax.bh. The other nice thing is that it only messes up the CX and DX registers, and we're no longer using those registers for anything. The other value we're interested in is in si.bl, so it won't be messed up. So once we've done that, we're actually already ready to write out the high word of our new x value. The low byte we'll have to hang on to for now, and we just move it into the BL register, and the BL that was from here, we just move that into BH, and we're also going to move SI into AX. So we now have the other value that we need to multiply by K in AX.BH again. So we can call our CORDIC mul on this. Once again, that'll multiply AX.BH by K, and so we're then ready to write out the result. So we write out the high word here, and the low bytes are now in the correct registers, BH and BL, and we just write them out at this line here. So now that value, xi, yi, has been transformed. It's now a rotated vector, and we've just written it straight back out to memory into those global variables, and so we're done with our CORDIC routine. That's really all there is to it. I told you it was simple. So the really hard part was actually writing that CORDIC mul that we did in the previous video. Well, at this point we're all ready to go ahead and actually start doing our animation with our new CORDIC routine. So of course we're going to be animating a line, and so I have a function here for drawing a line. This is one that we developed on the channel. So I can actually skip over all of this code because we've seen it all previously. Just draws a line in CGA mode 4, and I'll skip right down to where our main program begins, where the animation happens. So first of all, it goes into CGA mode 4, of course, and then I'm going to set up the initial coordinates of my line. Now, from the point of view of CORDIC, one end of the line is just going to be the origin. It's not going to change at all. It's fixed. And it's the other end of the line that we're going to rotate about the origin using CORDIC. So it's the coordinates of that endpoint that I need to put into these global variables that CORDIC operates on. Now, you remember those are 24-bit fixed point values, and the top 8 bits of those values are the integer parts. So when I put the coordinates 100, 0, which is the coordinates I chose for the initial position of that endpoint, when I put those into those 24-bit values, I have to put 100 into the top byte of the x coordinate and 0 into the top byte of the y coordinate. So that sets up the initial coordinates of the endpoint that we're rotating. And if we just call CORDIC on that, it'll do a rotation of that vector. Now I'm going to draw the line 10,000 times, and each time I'm going to rotate it a little bit by calling our CORDIC routine. And so basically the angle that it's going to be rotated by is theta, where tan theta is that 1 on 8 value that we chose. So first of all, in our loop, what we need to do is draw our line in its initial position before it's rotated. And then after it's rotated, we'll have to blank it out again before we redraw it in the new position. So let's draw it in its initial position first. And obviously, we don't want to use 24-bit fixed point values here. The line drawing procedure expects 16-bit integers. So we have to round those values to integers. And one way of doing that, because of this 2's complement representation, is just to add 0.5 to each of the values and then take the integer part. So that's what we're going to do. And adding 0.5 in that fixed point representation is just the same as adding 080 in hexadecimal to the second byte. And so it just means adding 80 in hexadecimal to the AX register and to the BX register, respectively. Now, I'm not modifying the original 24-bit fixed point values here. We only do this rounding of copies of that value that we made into registers because we don't want to mess up those really precise 24-bit values we've computed. So that's rounded the coordinates now up to integers, but these are signed integers. And so the first thing I need to do is to sign extend them. At the moment, the integer part is only in the top byte, so in the AH and BH registers. And I need to sign extend those out to 16-bit values, which is what the line drawing procedure expects. So obviously we're going to use CBW for that. It sign extends a byte to a word, in particular AL to AX. And so we put one of the coordinates into AL, sign extend, and then we switch them about so we can do exactly the same thing with the other coordinate and sign extend that to 16 bits. So now we have 2 integer coordinates in 16-bit registers. Now, of course, we need to shift everything so that we can actually see the animation. At the moment, we have one of the endpoints at 0, 0, and the other point is going to be rotating about that, and so 3/4 of the time it wouldn't be even visible on the screen. So I shift everything to roughly the center of the screen by adding, well, I chose to use 150 and 100 to add to the coordinates. That'll move it to pretty close to the center, not quite actually. And then we actually need to make a copy of our coordinates. Now, the reason we have to do this is because a little bit later we've got to blank this line out again when we're doing our animation before we redraw it in the new position. And so we're going to need these integer coordinates again later for the blanking. But notice that they're now unsigned values, and so what we can do is just take the low 8 bits and save those. That's all the information we need. And so I decided to put them into the DH and DL register and move it from there into DI. And I chose DI to save these coordinates because this is not messed up by the CORDIC routine. It's actually preserved by the CORDIC routine. So that means we can do our rotation and then restore our coordinates from the DI register. So let's go ahead and draw our line in that initial position before it's rotated, and we'll do that in color 2, and this is just a matter of pushing all the arguments onto the stack for the CGA line function. So these are the coordinates that we've just computed. This is the point that's being rotated, and of course the other end of the line is now at 100, 150. It doesn't move at all, so those are just constant values that we put on for those coordinates, and then we call our CGA line procedure and fix up our stack afterwards. So now that we've drawn our line in the initial position, we're all ready to rotate, and for that we just call CORDIC. Remember that CORDIC works with the values in those global variables, and so you don't need to pass anything on the stack here or fix the stack up afterwards. It's just call CORDIC, and now we get new 24-bit values for our rotated coordinates in those global variables. So now we're ready to blank out the line in its original position before we redraw it in the new position. And so we have to restore the coordinates from the DI register where we saved them, and then redraw the line in color 0. And so this is what this code is. It's exactly the same as what we had above, except it's now color 0 instead of color 2, because we want to blank the line out. But in between here I added some code for a delay, and I've commented this out because I want you to see what happens if there's no delay here. We'll come back to this delay a little bit later and see why precisely it's there. But that's actually the end of the loop. We're all ready now to redraw the line in its new position, and so we just go back to the beginning of the loop for that. That's where our color 2 line drawing is. So we just decrement our loop counter and jump back to the beginning of the loop, and that's it. So that's actually the end of the program. All we do now is just wait for key press, restore the video mode, and go back to DOS as normal. And so let's actually save this and assemble it and link it, and then we can see how it performs. So link CORDIC 1, and let's actually run it. And I don't know how well this is going to show up. It's rotating so quickly here, even with the naked eye. I'm just seeing little fragments of line appearing, and actually it's really doing numerous rotations before the line shows up again. That's how fast it's going. One frame of the CRT is just too slow compared to our line rotation. So we're getting really amazing performance here, and actually I had a little bit of trouble calculating just how long the actual rotation itself takes. If you just draw the lines and don't do the rotations, it takes about exactly the same amount of time to run the code. So it really is going incredibly fast. So now let's put that delay in and actually see what it looks like. Well, I've gone ahead and uncommented that delay so we can see what's going on, and I've rebuilt the program, so let's run it and see what it looks like now. So this time you can see all of the iterations. You probably still see the line on the screen multiple times per frame. I think that's just because this emulator I'm using is trying to simulate a CRT that has a slow refresh rate or something like that. But anyway, you can actually see the line rotating by the same amount each iteration, that angle theta, where tan theta equals 1 on 8, which we hard coded in. So we're kind of stuck with the angle we're rotating by each time. But again, if this is all you want to do, just rotate an object on the screen, you don't really care that much about what angle it is, you just want it to look nice, then this is an extremely fast way of doing it. As you saw, we had to slow it down, it's so fast. But the other remarkable thing about this is just how accurate it is. I did a calculation, I think with that 24-bit approximation we're doing, we lose something like half a pixel per 10,000 iterations, which is really incredible. So you can rotate an object for a long time like this. So if we've got really good performance and we have great accuracy, can we use this for 3D rotation? And the answer is yes and no. So obviously, if you use the X and Y axes, just like we currently are, and do a rotation of all of your points, then that's equivalent to a rotation about the Z axis. So you can do a 3D rotation in that sense. You could also switch the axes about and do a rotation about the Y axis or about the X axis. And then you could even combine those. You could do one of the iterations to rotate about the x-axis and another one to rotate about the y-axis and get a different kind of rotation again. Or do the same thing for the x, y and z axes. And you could even use this routine multiple times for rotation about one of the axes, and then just use it once for rotation about each of the other axes and so on. So different combinations would give you different rotations. But in the end, what you'll find is that no matter what combination you pick to use, you'll only end up with a rotation about a single axis. Now, this time it won't be necessarily a coordinate axis, but there will be some axis in space going through the origin about which your object will rotate. Now, so I call this single axis rotation, but it turns out there are actually other kinds of rotation that you can do, and it's even hard to visualize what these might be unless I had a cube on the screen that I could actually do this to and show you the difference. And I call those 2 and 3 axis rotations. And it turns out that you can't do those with this simple CORDIC trick that we used. You actually need a full CORDIC implementation for those, because you essentially need to compute the full rotation matrix. You'll need sine or cos or both. And for that we need the full CORDIC implementation, because we actually have to rotate there with arbitrary angles theta. And so this is really a topic for a later video, and we'll certainly deal with that eventually, this 2 and 3 axis rotation. In the medium term we'll do single axis rotation, and we'll show you what that looks like, and for that we don't need anything more than what we have here, at least if we don't care too much about the angle. But there are actually a couple of other things I want to cover on the channel before we get to that. So we're going to take a break from CORDIC for a while, and we'll come back to the 3D rotations in a later video.